And discuss intermolecular forces, the forces between molecules. So these are not the bonds within a molecule, these are the forces between molecules. So if I have two methane molecules, which in 3 dimension take on this tetrahedral shape, so here's one methane molecule, and here's a second methane molecule. So there's covalent bonds between the carbon to the hydrogen. Carbon to the hydrogen, carbon to the hydrogen, carbon to the hydrogen. There's 4 covalent bonds, but between the molecules themselves, there's a force of attraction called dispersion forces. So dispersion force is one of my 3 intermolecular forces. So there's dispersion, there's dipole-dipole, and hydrogen bonding. Those are the 3 intermolecular forces. And I've written them in order from weakest to strongest. Hydrogen bonding is the strongest intermolecular force. So when we boil or melt either a liquid or a solid, we're breaking intermolecular forces with heat because that's a physical change. So allowing the methane to boil separates these molecules and allows them to float up as a gas in the air. But there's still that methane molecule. We're not breaking the bonds within the molecule. That's bond energy. So that would actually be a chemical change if we were breaking the bonds. Breaking the intermolecular forces is just a physical change that just requires heat. Even though one of the forces is called hydrogen bonding, it's not a bond, it's a force. So they're relatively weak, and we have to remember that they're what holds those molecules next to each other, but they're not the bonds themselves. So if we boil water, which has that bent shape using our Vesper model, we're going to break our intermolecular forces of dispersion, dipole-dipole, and hydrogen bonding when we boil water, allowing each of these free individual water molecules to float away as a gas. So again, the strongest intermolecular force is hydrogen bonding, but that one only occurs when you have an NH, OH, or FH bond. Dipole-dipole occurs only for polar compounds. So you have to determine if it's a polar or not polar compound to determine whether or not it has dipole-dipole. And London dispersion forces, which chemists typically call just dispersion forces, are just for every different type of molecule. So nonpolar molecules have just dispersion forces, but every single type of molecule has dispersion forces. Every molecule always has dispersion forces, so you always list that as one of your intermolecular forces. And dipole-dipole being only for polar molecules means that nonpolar molecules will not have dipole-dipole. Hydrogen bonding, they have to be polar molecules that contain one of those NH, FH, or OH bonds. And dispersion forces, since everything has them, so polar molecules and nonpolar molecules also have them. Dispersion forces increase as the size of a molecule increases. So the larger the molecule, the larger the dispersion forces. So let's think, how would the strength of intermolecular forces affect melting and boiling points? So again, the more intermolecular forces we have, the higher the melting and boiling point. And if we're comparing compounds that have just one force each, then we have to look at the size of the compound itself. The larger the compound, the greater the dispersion forces. So if we're looking at comparing molecules, we have to be able to answer, can the molecules form hydrogen bonds? Again, that's only if they have an NH, FH, or OH bond. And hydrogen bonding is a special case of dipole-dipole. That's an extra strong intermolecular force. So if we look at something like this, where we're plotting boiling points, with all the different groups. Okay, if you look at water, hydrogen fluoride, and ammonia, they have extremely high boiling points. They don't seem to match the trend on this graph. And that's because they have that extra intermolecular force of hydrogen bonding due to having an NH, FH, or OH bond. So having that extra intermolecular force raises their boiling points so that they are much higher than we would expect without having hydrogen bonding. The more intermolecular forces, the higher the melting or boiling point. So if we see that a molecule is polar, we will know that it has dipole-dipole forces, and dipole-dipole forces are one extra force compared to just having dispersion forces. So in that previous one where we had methane, which is a tetrahedron, having just dispersion forces because it's a nonpolar molecule. Okay, I know that because taking my delta En between carbon and hydrogen gives me between 0 and 0.5, which is a nonpolar covalent bond. So my electronegativity difference between carbon and hydrogen tells me that they share that pair of electrons evenly. If I were to get a value between 0.5 and 1.7, that would be a polar covalent bond. And then greater than 1.7 is an ionic bond. So if I get a polar covalent bond, then I have to check and see if my polar bonds cancel out. So here I don't have any polar covalent bonds. So right away it's a nonpolar molecule. The entire molecule is nonpolar, which means the only intermolecular force that I can list for it is dispersion. One force. If I now draw carbon, 3 of these are still hydrogens, but I convert one of the hydrogens is now a chlorine. Okay, so I have chloromethane here. Now, this delta En between carbon and chlorine is in this 0.5 to 1.7 range. This is a polar bond. Because there are no other polar bonds that will cancel this out, it's a non-symmetrical molecule, and it is a polar molecule since I have only one polar bond. So if I have more than one polar bond, I look and see if those polar bonds cancel each other out. But here I only have one polar bond. Nothing can cancel it out. It's a polar molecule, so that means it has dispersion as one of its intermolecular forces. It also has dipole-dipole because it is a polar molecule. Okay, dipole-dipole. My pen's not working very well, but. So the more intermolecular forces, the higher the melting and boiling point. Therefore, this would have a higher melting or boiling point than my nonpolar methane because it has 2 forces between all of its molecules versus just one force here of dispersion. Now, if I had something that also had hydrogen bonding, then that would be 3 forces versus 2 forces, and 3 forces would be an even higher melting or boiling point than having 2 forces. So having 3 forces, like hydrogen bonding as my third, again gives me a higher melting or boiling point. If I just have dispersion forces, then I am looking at the size of the molecule itself. The larger the hydrocarbon, the greater the dispersion forces, therefore the greater the melting or boiling point. As I can see, C8H18, so my octane is a larger boiling point than my methane because it's got more carbons. That's the only difference. They both have only one intermolecular force of dispersion, but more carbons, greater dispersion forces, therefore greater melting or boiling point. Okay, so now when you guys draw the intermolecular forces here, I want you to try drawing at least 2 molecules like I did in the above example to show the intermolecular forces between them and label them. So I'm just quickly going to do HBr with you. I only have the one bond, and I look and see that in fact it is an electronegativity difference between 0.5 and 1.7. So I'm just checking my delta En. So for hydrogen, my electronegativity is 2.1, and for bromine, my electronegativity is 2.8. So 2.8 minus 2.1 equals 0.7. So it's in that 0.5 to 1.7 range, which means it's a polar bond. So I have a polar bond here. And since there's only one polar bond, there's nothing that can cancel out that polar bond. It's a non-symmetrical molecule, which means it's a polar molecule. And polar molecules always have dispersion. They also have dipole-dipole. Now, the third intermolecular force is hydrogen bonding, but that's only for molecules that have NH, OH, or FH, which I don't have here. So HBr has two intermolecular forces, dispersion and dipole-dipole. So that's what you should do for the rest of these. And once you do that, you can rank these according to what you think would have the highest boiling point based on how many intermolecular forces it has. The more intermolecular forces, the higher the melting and boiling point. This chart here is for you to fill out using the textbook to figure out the description of all of our intermolecular forces and what the definition is of all of these. Okay, then you can run through these examples trying to figure out what is most soluble in water. So remember that hydrogen bonding will be formed between something that's soluble in water, between water and itself. Also, polar molecules are able to dissolve in water because of the whole like dissolves like. Some of these are written in the old IUPAC system, like 1-propanol is actually propan-1-ol. It's just like I told you guys, reverting back to the prior to 2010. And this is a really great chart telling us what has the most intermolecular forces, therefore the highest melting and boiling point. So primary amides are at the top of this list, followed by secondary, tertiary amides, then carboxylic acids, amines, alcohols, alkyl halides, esters, aldehydes and ketones, ethers, and hydrocarbons. So organic compounds are easy to rank because they're in this chart, so we know exactly how many intermolecular forces they have. All of our inorganic compounds, we have to draw using our Vesper theory and then compare their intermolecular forces from one to another to see how many they have.